Hello and welcome back to Psychology 301. This is Dr. Williams, and this is lecture 3 in a series of lectures on stimulus control. Today we're going to talk about discrimination and peak shift and Kenneth Spence in particular. So we've already talked about and described what peak shift is, and so what I'd like to do is talk a little bit about how Kenneth Spence put forth a theory to explain how peak shift occurs. So let's start out with a little introduction. Kenneth Spence was a very well-known and well-respected psychologist in the middle of the 20th century. He studied under Robert Yerkes at Yale University. He studied discrimination learning at the National Research Council at the Yale Laboratories of Primate Biology. He then moved to the University of Iowa, where he studied motivation with Clark Hull. He received the very first Distinguished Scientific Contribution Award in 1956 from the APA. He was very, very well respected. And he is listed as the 62nd most cited psychologist of the 20th century. So you have to understand that this includes people like Abraham Maslow and Sigmund Freud and Erik Erikson and all the famous psychologists that you've learned about. He's number 62. So up there, lots of publications, well-known and well-respected, and a real hardcore scientist. So basically, he said several things about generalization gradients within a single dimension. First of all, reinforcement in the presence of an S plus is both necessary and sufficient to produce stimulus control and to produce that classic peaked gradient. So he basically said that single stimulus training is all that's required to get a peaked generalization gradient. He also said that stimulus control, the reason you get the peaked gradient is because that the stimulus control that's established by the S plus spreads to other similar stimuli or generalizes to other similar stimuli in a manner that's proportional to their degree of similarity with the S plus. So stimuli that are more similar will get greater responding or greater stimulus control, and stimuli that are more different will get less stimulus control. All right. He also said that an S minus is not necessary for a peaked gradient to emerge. So you can get that nice peaked gradient like the Gutmann and Kalish gradient with just an S plus alone. And then finally, he said that, however, if you do introduce an S minus, it's going to result in a gradient of non-responding, similar to an inhibitory gradient, and that inhibitory gradient is going to compete with the excitatory gradient from the S plus, and they're going to compete with respect to the tendency to respond. And we're going to go into a lot more detail on this. Okay, so let's talk about Spence's theory of peak shift. Spence basically said that discrimination training, where you use both an S plus and an S minus, S plus predicting reinforcement for responding, the S minus predicting no reinforcement for responding, will produce two competing gradients. The S plus is going to create an excitatory gradient, a tendency to respond that is centered on the S plus. And the inhibitory, the S minus, is going to create a tendency to not respond that's centered on the S minus, and he called that the inhibitory gradient. And he said these two gradients are going to compete inside the organism, and what we see in terms of behavior is going to be the net result or the compromise between these two competing response strengths. So here we go. Let me describe this theory with pictures from your book. So he said if you have an S plus alone, here at 550 nanometers, you're going to get this green gradient. You're going to get a gradient that is centered. The highest point of the peak will be over the S plus. So you get this green gradient. And if that's all you did, that's where your responding would be. With an S minus, you're also going to create an inhibitory gradient that is centered on the S minus. So here it is at 590, and we're going to have an S minus, and so you're going to get the least amount of responding, or the least tendency to respond, around that S minus that will start to dissipate as you move away from your S minus. Okay? So we put those together, and you end up with an excitatory gradient inside the organism, right? Excitation, S plus, I'm excited. Stimuli around it, I'm excited. And an inhibitory gradient around the S minus, which is, oh, I really hate that S minus, I don't want to respond. And these two gradients will compete. They overlap, and so the desire not to respond will suppress some of the desire to respond, and so we end up with a gradient that is suppressed from this point over because it's in competition with the S minus. And so what we see is this, the difference is the actual responding that we see, these dark boxes, the black boxes. So here's a question. When do you think the two overlapping gradients will compete the most? In other words, when the S plus and the S minus are more similar, will there be more competition? Or when the S plus and S minus are more different, will there be more competition? Well, think back to the Hansen study from 1959, and remember that the answer has to do with how difficult the discrimination is between the S plus and the S minus. So I'll come back here just for a moment. So here we have 550 is the this is the S plus, 590 is the S minus. When would these two overlap the most? When they're farther apart or when they're closer together? Well, the answer is the two overlapping gradients compete the most when the S plus and the S minus are similar, when the discrimination is difficult. So when the S plus is really similar to the S minus, it makes the telling the difference between them more difficult, so you get more overlap. So the closer they are to each other, the harder the discrimination is, the more the gradients overlap, the greater the competition between the two gradients, and therefore the bigger the peak shift. Let me show you how this works. All right, so here's your excitatory gradient. This is tones, and we've chosen 8 kilohertz as our S plus. So here's our S plus, and we get a peak over the S plus. All right, and now we introduce an S minus, and the S minus is up here at 18 kilohertz. And so we have this tendency to not respond. Here we have excitation, here we have inhibition. So our inhibitory gradient here peaked over 18 kilohertz, which is our S minus. So when we put these together, we now have both gradients, an excitatory gradient over 8 kilohertz, or S plus, an inhibitory gradient over 18 kilohertz, which is our inhibitory gradient. And we can look at how they overlap. So here is where they overlap the most, is in this region of blue, is where we get the most amount of overlap. You'll notice on the other side, we have almost no inhibition from the S minus, and way out here, where it ends here, we see there's very little excitation. So it's between those two areas where we see the greatest amount of competition, and what that's going to do is it's going to pull down, we're going to get an averaging effect, and so we're going to get an average, this is where where we have our competition overlap, and there's very little suppression here. There's just a little bit at one end. Now, let's go back to the beginning. Again, here's our S plus at 8 kilohertz. Here's our S minus at 18 kilohertz. And what I'm going to do is I'm going to move my S plus closer to the S minus closer to the S plus. So I've now shifted from 18 kilohertz. My S minus is now at 14 kilohertz. So the peak is now above the S minus at 14 kilohertz. There's clearly more overlap. So now we have a greater amount of overlap, and what you'll notice is that the suppression from the S minus pulling down on the from the inhibitory gradient pulling down on the excitatory gradient gives the impression of the peak moving because it's suppressing everything else. So you'll see that as we get closer, the peak keeps shifting. Now, it's not actually shifting. What's happening is that the peak appears to shift because the rest of the excitation is suppressed by the inhibitory gradient. Here we're going to move it again. So even more similarity. Now we've moved the S minus to 12 kilohertz. Now it's overlapping a huge amount. You see how huge the amount of overlap is? And it pulls down and suppresses behavior almost completely. So here it looks as though the peak has moved way over. So the more they overlap, the further the shift. I hope you can see that. So now the question becomes, can you actually see an inhibitory gradient? Well, back in 1963, Honig and Pennypacker and a couple of their students conducted an experiment to see whether they could actually measure responding to an inhibitory gradient. So they used two groups of pigeons. Group one, well, actually both groups are going to see a white key light with a vertical line on it. Now, group one, the S plus is the vertical line, and when the vertical line is absent, it's the S minus. So just the white key light by itself is the S minus, but the white key light with a vertical black line is the S plus. So when they see a vertical line, they want to respond, you get excitation, and when you have just a white key, they don't like it. Group two, they also see a white key with a vertical line or just a white key, but now it's reversed. S2, the S plus is just plain white. As long as it's just white, you get responding. However, the S minus is a white key light with a vertical line. And so they train both of these groups for 7 to 10 days until they get really good control by the S plus and control by the S minus in that they don't respond to it. So they exposed the birds to all different line tilt stimuli. So here are examples. And the lines, here's the S plus, the vertical line, or the S minus, depending on which group. But then they would tilt the line gradually away to horizontal in either direction. And this is what they use to test stimulus control by the vertical line. So the results are that group one shows an excitatory gradient and group two actually shows a measurable inhibitory gradient. When they measured, they're responding in extinction to all the different line tilt stimuli. And they included in their study a replication so they could demonstrate that their findings were not simply an anomaly. So here are the data. Here you can actually see the excitatory gradients and inhibitory gradients. I've highlighted them in color so you can see them. There are two studies. There's study 1 and study 2. And for both of them, up here what says line positive means that the horizontal line is the S plus and line negative is that the horizontal line is the S minus. And so the green excitatory gradients, you can see the first one here from study 1. The peak is directly over that 90-degree vertical line, and exactly where you would expect it. The same is true for the second study. Here, this is the line positive, so this is the S plus, again, over the 90-degree tilt. But what's really important here are the inhibitory gradients. Remember that the key lights are white, and the line orientations are superimposed on the white key lights. So even though in the cases where you have the S minus is the vertical line orientation at 90 degrees, the remainder of the key is still a white key light. So you get some responding. The lowest amount of responding in both studies is directly above that 90-degree line tilt. So here's study 1 and study 2, but then they measured responding in each of those in either direction. And what you find is that the tendency to respond to the white aspect of the key light increases as you move away from that 90-degree vertical line. So this shows us, I mean, this is quite extraordinary. They actually were able to directly measure an inhibitory gradient. These data profoundly supported Spence's view. So Spence's theory of discrimination made three major points, two major points with an extension, I guess. First of all, a peaked excitatory gradient can be established with an S plus only. No S minus is needed. Now, as part of that, he says that the tendency to respond to other stimuli generalizes from the S plus, and that tendency is innate. It just happens. That generalization to other stimuli is innate. He also said that the same is true for inhibitory gradients. So the inhibitory gradient forms around the S minus, and the tendency to not respond generalizes based on the similarity with the S minus, and that is also innate. And finally, that these two gradients, the excitatory gradient and the inhibitory gradient, interact in a competing fashion to produce the peak shift phenomenon. So, in that whole theory, he makes two major claims about generalization gradients. The first one is that excitatory and inhibitory stimuli can be established around an S plus or an S minus, and that the tendency to respond or not will generalize within a stimulus dimension, and that tendency is innate. There's a little something missing here. There we go. And so it's this idea that stimulus control spreads to other stimuli in the dimension in a fashion that's proportional to the stimulus, the training stimulus, and that tendency is innate was one of his major conclusions. The second conclusion was that excitatory and inhibitory gradients interact in a competing fashion, and that's what's responsible for producing the peak shift phenomenon. Now, I'm going to stop there because that's enough for one lecture. That's a lot to digest. But next time we're going to talk about testing Spence's conclusions. He made these predictions without ever testing them. And it wasn't for another 20 years that we see a direct test of Spence's ideas.